Hello everyone. In today's session, we are going to discuss about VSEPR theory, that is valence shell electron pair repulsion. This was given by Nyholm and Gillespie, and this is an important model in order to predict the molecular geometry. The electrons around the central atom present in the valence shell, they tend to be in a position that gives minimum repulsion to each other, in order to which it affects the molecular geometry. So let us explore the concept VSEPR. Hello everyone. Today's discussion is on valence shell electron pair repulsion. That is, the repulsion between the electrons that are present in the valence shell of molecules. Now, Lewis' concept was not enough to explain the shapes of molecules. For that, we needed a new model, which is the VSEPR model. It was given by Sidgwick. It was actually rectified and it was modified rather. Okay, by Nyholm and Gillespie, but Sidgwick and Powell in 1940 had worked over it. See, it was developed and redefined by Nyholm and Gillespie. So, though we name Nyholm and Gillespie to actually modify it, but the initial work was done by Sidgwick and Powell. The main postulates of VSEPR theory are: shape of molecules depends on, the shape of the molecule is actually dependent on the number of the valence shell electron pairs. That is, how many electron pairs are there, whether it is bonded or non-bonded. Non-bonded means it can exist as lone pairs around the central atom. Pairs of electrons in the valence shell, that means the electrons in the valence shell, they repel each other, and for which they try to occupy maximum distance between them in order to minimize the repulsion when they are oriented in space. The valence shell is taken as a sphere with electron pairs localizing on the spherical surface at maximum distance from each other. Now, if there is a multiple bond like CO2, SO2 molecules, then the multiple bond is also treated as a single electron pair. Like if I say CO2, so we are having multiple bond of with carbon and oxygen, amongst carbon and oxygen, but they are treated as two electron pair. So it has a linear structure. Okay, when two or more resonance structure is possible, then the VSEPR model is applicable to any such structure. Now, the repulsive interaction, we said what? The valence shell electron, they have repulsive interaction amongst them. Why do they have repulsive interaction? Because they are all electron clouds. So, if electron clouds are close to each other in three-dimensional structure, they will have a tendency to repulse each other because they are all negatively charged. So when they repulse each other, the structure gets oriented to the geometry where the repulsive interaction is minimum and the stability is maximum. So we have seen, as per VSEPR, that the repulsive interaction between the lone pairs are maximum. So a lone pair repulsion is greater than a lone pair bond pair repulsion and is greater than a bond pair repulsion. Now, Nyholm and Gillespie refined the VSEPR model by explaining the important difference between the lone pairs and the bonding pairs of electrons. Initially, all were taken as electron pairs. Later on, it was actually the work of Nyholm and Gillespie that has actually made it what? The electron pairs are both. That means the bonded pair of electron as well as the non-bonded pair of electron. So I will say the bonded pair of electron and the lone pairs. Together, they form the electron pair. And the geometry is on account of the electron pair, in order to give minimum repulsion to the molecule. Okay. So here are the geometries that we have seen without lone pair around the central atom. all are bond pairs like AB2, AB3, AB4, AB5, AB6. See, none of the molecules are having lone pairs. They are all the bond pairs only. So if I say this is AB2, central atom is A and these are B. So it is BeCl2. So without any lone pair. You know that how it is because you know the valence electrons, the valence shell electrons of beryllium are 2. And so what is happening? There is no more lone pair left. Now BF3, it's of the type AB3 type. So where the central atom is A and these are the 3B. Okay, so this is AB4 type. What are the names of the geometry? This is AB5 type. None of them have any lone pair. So I can say over here, there are no lone pair in these structures. So this is a linear structure, BeCl2. AB3 is a trigonal planar structure. See, in a linear structure, the bond pairs are at a maximum distance. So the bond angle is 180 degree. And in case of BF3 or AB3 type, the bond angle will be 120 degree in order to give minimum repulsion. Trigonal planar geometry. And AB4, this is a tetrahedral geometry where each angle is 109 degree 5 minutes. Okay, 5 degree, 109.5 degree or 109 degree 25 minutes. Okay. So now this is what again AB5 type of molecule, which is known as TBP structure, trigonal bipyramidal structure. In a TBP structure, there is a speciality, tetrahedral structure. You know what? That in a tetrahedral structure, the bond angle is 109.5 degree. But in a TBP structure, there are two different types of bond angle we can see. One is a 90 degree and the other is 120 degree. Why? Because actually it is like this. A, the central atom, has three type of same bonds and these bonds are known as equatorial bonds. They are known as equatorial bonds and the other two bonds are known as axial bonds. Okay, so they are known as axial bonds. There are two types of bonds. So these three equatorial bonds form the trigonal planar form, and perpendicular to the trigonal plane, there are the two axial bonds. So these are the axial bonds and these three are the equatorial bonds. In a TBP structure, see, the equatorial bonds experience less repulsive interaction. Only they experience repulsive interaction between, each equatorial bond is experiencing repulsive interaction of 290 degree repulsive interaction. But the axial bonds are experiencing so many 3 repulsive interaction. So the number of repulsive interaction experienced by the axial bonds, they are greater than the number of repulsive interaction experienced by the equatorial bonds. So what happens is the equatorial bonds, since the repulsive interaction is less, the stability is more. So in a TBP structure, the equatorial bonds are more stable than the axial bonds. And on account of greater repulsion experienced by the axial bonds are longer than the equatorial bonds. So I have said two important things regarding TBP structure, a trigonal bipyramidal structure. Number one is there are two types of bonds. There are 3 equatorial bonds forming a trigonal plane, and there are 2 axial bonds which is perpendicular to the trigonal plane. The equatorial bonds are more stable because they experience less repulsive interaction. The axial bonds are less stable because they experience more repulsive interaction, and for which Just because it experiences more repulsive interaction, the axial bonds are longer than the equatorial bonds. And equatorial bonds are more stable than the axial bonds. Okay, these two important points I have told you. Next, let us see the examples in a tabular form. Geometry of molecules in which the central atom has no lone pair of electron. So bond pair, as many bond pairs are there, that is only the electron pair. So this electron pair is actually the bond pairs because there is zero lone pair. Okay, so this is what type? This is, we can see, AB2 type. Okay, so this is AB2 type and it can have 180-degree bond angle, linear structure. These are the examples. Now, when there are three electron pairs, three bond pairs, AB3 type, it can have what? I said trigonal planar and the bond angle is 120-degree. Okay, so next, moving on to AB4 type, I said tetrahedral geometry, and so this is the regular tetrahedron. Why I'm using the term regular tetrahedron? Because the central atom is actually surrounded by similar, or rather same atoms. All are B. So the geometry is not a distorted geometry, it's a regular geometry. If there is a lone pair present, then the geometry becomes distorted and it is not a regular geometry. Okay, so bond pair or electron pair 5 means AB5, which just now I said a TBP structure, trigonal bipyramidal structure with three types of three equatorial bonds, and there are two axial bonds, and the axial bonds are less stable and longer. So what about the axial bonds? They are less stable bonds and of course they are longer than the equatorial bonds. Okay, example is PCl5 without any lone pair. Next, moving on to electron pair, which is 6, and so I can say it is AB6 type and it is an octahedral geometry. Remember one thing, that in octahedral geometry we have a square plane. This is your square plane. Okay, and now these are the equatorial bonds, like, okay, square planar geometry. But when I have two more here, the axial, so here I will say the axial bonds are more stable. Okay, so like in in TBP structure, the equatorial bonds were more stable. Here in octahedral geometry, the axial bonds are more stable, because you see here the angle has reduced. In a square plane geometry, the angle has reduced. It has become 90-degree where it was 120-degree. So the repulsion for a 120-degree was less and the repulsion for a 90-degree has increased. So this plane has actually greater repulsion, and so the most stable is the axial one. Example is SF6. Okay, next we go to the shape or the geometry where with central ions having one or more lone pairs of electrons. So here we can see AB2E type. E means the lone pair. Okay, so this is the lone pair. So AB2, from this I can see there are two bond pairs, there are one lone pair, and combining I have three electron pair. So if the electron pair is 3, then obviously it will be like AB3 type of geometry. And so what do I expect? AB3 type of geometry means I expect a trigonal planar form. Spelling should be NAR. So trigonal planar form. So one will be the lone pair, rest will be the I'll say the bond pairs. But remember, a lone pair is present, so the repulsion on account of the presence of lone pair, which is a lone pair 2 bond pair repulsion, is greater than a bond pair 2 bond pair repulsion, for which the bond angle contracts. This bond angle will be now less than 120 degree. and so the structure, or rather I'll say the shape, structure is trigonal planar, but the shape is what? Is a bent shape, or it can be also called a V shape with a bond angle which is less than 120 degree. Okay, so this is SO2. The examples are SO2, O3, and multiple bond is treated as a single bond. That means bond pair only. Okay, so let us see the other one. Here I have one lone pair. This is one lone pair. Okay, this is one lone pair. Bond pairs are 3. Total electron pairs are how much? 4. So for 4 electron pair, I will say AB4 type with a lone pair. That's why AB3E is written. No. So AB4 type means it will have a tetrahedral geometry with a lone pair in one of the position. Now this lone pair will again exert lone pair bond pair repulsion, which is greater than the bond pair repulsion. So this will not be a tetrahedral, but it will be a distorted tetrahedral. So after that, due to the distortion, the shape is known as trigonal pyramidal, which is seen in NH3 because nitrogen has a lone pair. Same thing is seen in PH3 as well. Okay, but I will discuss about the bond angle later on regarding NH3 and regarding PH3. So NH3 has a trigonal pyramidal structure. PH3 also has a trigonal pyramidal structure, but the bond angle differs. Why it is so? What is the reason? That I will discuss later on. Now, this is again 2 lone pair and 2 bond pair, giving rise to 4 electron pair again. But keep in mind that there are 2 lone pairs. So this is a 2 lone pair. So here we have a lone pair, 2 lone pair repulsion, which is greater than a lone pair, 2 bond pair repulsion, which is again greater than a bond pair, 2 bond pair repulsion. So this is the lone pair repulsion. Now here again is the lone pair bond pair repulsion, and these are the bond pair repulsion. But since this repulsion is greater, so there is a contraction in the bond angle. Which bond angle? Angle BAB bond angle. There is a contraction. The expected bond angle was 109 degree 28 minutes, or it is 109.5 degree, but in H2O it is 104 degree, almost 104.5 maybe. So which is very much less than 109 degree 28 minutes, or maybe 109.5 degree. Okay. So now here again we can see trigonal bipyramidal structure, TBP structure. Why TBP structure? Lone pair is 1, bond pair is 4, electron pair thus becomes equal to 5. 5 means a TBP structure. Now in a TBP structure, equatorial position is a stable position, so the lone pair has occupied the equatorial position because it experiences less repulsion. Okay, so on account of which there will be little bit of distortion between the lone pair and the bond pair. Okay, for which it actually gets little bit bent, and this is known as a seesaw shape, and it is seen in SF4. See, sulfur has 6 valence electron, out of which 4 are used in bond pair. Okay, now leftover is 2 electron. That means it exists as one lone pair. Okay, like this you can also see. Suppose it is not being told, suppose ClF3, you have been told that ClF3 is given. You have to predict the structure, the shape of ClF3 based on VSEPR. How to proceed? Now the central atom is the less electronegative one. So of course fluorine is not the central atom, Cl is less electronegative, so this Cl will be the central atom. Okay, so this is actually a polyhalogen compound because more than one halogen is there. So here we can see Cl is central atom, for which the number of valence electron for Cl is 7. Now what happens is bond pair, here there are ClF3 bonds, so 3. Now we will do 7 minus 3, that is 4, which remains as a pair. So divided by 2, which is equal to 2 lone pair. So 2 lone pair, 3 bond pair, so electron pair is equal to 5, and expected is a TBP structure. Remember that the 2 lone pair will occupy the position which is more stable and experiences less repulsion. That is the equatorial position, and this is the equatorial position. Can you see that there are 2 lone pairs for which that will experience lone pair repulsion, but the shape is a clear-cut T shape. Okay, remember that when you actually predict the structure, you predict the geometry, you include the bond pair as well as the lone pair. That's why I said TBP structure along with 2 lone pair and 3 bond pair. But when I'm talking about the shape, I have to omit the lone pair and see what shape is obtained by only the bond pairs. Okay, like in seesaw also I said for SF4. Now the structure or the geometry was a TBP, but the shape was like a seesaw because I am going to see only the bond pairs in that case. Now here it is like BRF5, bromine. Same case again. Here bromine has what? Bromine has 7 valence electron. There are how many bond pair? Bond pair is equal to 5. So now bond pair is equal to 5 means 7 minus 5 is 2 electron left. So I can have only one lone pair. 2 electron will form one lone pair. So it has one lone pair and it has 5 bond pair. Total number of electron pairs are equal to 6. That means octahedral geometry. And in octahedral geometry, I have told you the axial positions are most stable positions. So the lone pair is oriented here in the axial position. And see, leaving the lone pair, the other part, it's a square pyramid. It's a square pyramid. Okay, so that is the shape. Next, moving on to another type, XeF4, xenon. Xenon is noble gas. Now, people say xenon is a noble gas, but it is reacting. Yes, dear, because xenon is actually very low in the group. Its size is more. So, xenon has reactivity. It can form compounds. Here again, AR. Okay. It can form compounds with fluorine, forming xenon fluorides, xenon oxyfluorides, xenon oxides. These are the things that can xenon form. Now xenon is noble gas, so it has 8 valence electron, out of which there are bond pairs equal to 4. So 8 minus 4 is 4 by 2, so there will be 2 lone pair. So I have 2 lone pair, 4 bond pair. Again I'll say number of electron pair is equal to 6. So 2 lone pair will occupy the axial position that experiences less repulsion. Now leaving the lone pair, only the bond pair will give a square planar shape. That's why it has a square planar shape. Okay. So now we were talking about multiple bonds behaving like a single bond pair. So let us see that number of bond pairs here, it is 4. Okay. So A, B to E, that means 2 bond pair and 1 lone pair. But they have written number of bond pairs equal to 4. Why? Because there is a multiple bond, but they are treated as 1 bond pair, 2 bond pair and 1 lone pair. So if it is so, it will be what? 3 bond pair. Sorry, it is a 2 bond pair and one lone pair, which gives rise to 3 electron pair, and so it will have a trigonal planar geometry. See, it's a trigonal planar geometry, but it's a double bond, na? So for that reason, and it also has a lone pair. So for that reason, there will be a lone pair bond pair repulsion. This is a lone pair bond pair repulsion, which is obviously greater than a bond pair repulsion. And when you talk about a trigonal geometry, trigonal planar geometry, what is the expected bond angle? It's 120 degree. But the actual angle, you can see it's less than that of 120 degree on account of the repulsion that is faced by the lone pair and the bond pair. Next is the NH3 molecule over here. It's having a trigonal pyramidal because of the lone pair and the bond pair repulsion. Same thing, the bond angle is expected to be tetrahedral structure, so 109 degree 28 minutes or 109.5 degree, but it is 107 degree, which is less than that. So next one also same thing, H2O. H2O has 2 bond pair, 2 lone pair, so it has actually 4 electron pairs, and 4 electron pairs means what? Tetrahedral geometry. So here the tetrahedral geometry, expected bond angle 109 degree 28 minutes or 109.5 degree, but actually it is 104.5 degree because there are 2 lone pairs, and so here there is not only lone pair bond pair but a lone pair repulsion, which is way greater than a lone pair bond pair repulsion and greater than a bond pair repulsion. So in NH3 the bond angle was 107 degrees because there was only one lone pair and there was only lone pair bond pair repulsion, but in case of H2O there are 2 lone pair and there is lone pair repulsion. Now over here we can see it is what? SF4. So SF4, which is possible? Sulfur is the central atom. So 6 valence electron. Bond pairs. How many bond pairs are there? 4. Fluorine. 1 electron it gives, na? So it can be 4 bond pair. So 6 minus 4 is 2. So how many lone pair can be there with these 2 electrons? There will be only 1 lone pair. So I have 1 lone pair. I have 4 bond pair. So together I can say I have 5 electron pair. So it gives a TBP structure. And in a TBP structure, the equatorial position is a more stable position, and so the lone pair will be oriented in the equatorial position in order to experience less repulsion. So it is a seesaw shape. Okay. So this is the part of NCERT. Here again we can see what is happening in CLF3. So I said the 2 lone pairs will be in the equatorial position. So these are not the probable structures. This is the probable structure with a T shape. Okay, because I have 3 bond pairs, 2 lone pairs, so 5 electron pair, which means a TBP structure, and in a TBP structure both the lone pairs will be oriented in the equatorial, which is more stable. This is another resource from which we can see the topic. So when you are growing up, you are now class 11. So when you are doing higher studies, you have to explore more. You have to explore more and more resources. Okay. So let us see. But as a CBSE student, I will say your first and foremost book will be your NCERT book only. Now, we have seen the basics from NCERT book. Same thing is here. VSEPR theory, what are the postulates, everything is here. Okay. So I will just tell you to go through this and see what are the structures, if anything extra you people get. But here till where I am scrolling, you will not get anything extra. I'm telling you where you will get extra. This example, square pyramid example of IF5 is extra. SiF4 is extra. H3O plus extra. So go through these things, okay, such that you know how to draw the structures of these. This is a question. Now here BRF5, this also BRF5, IF5, these all things. Xenon compounds we have already seen. So not to see this. Next, we are moving to this part, which is not there, but it is there as a question in NCERT. That is, when you see the bond angle H2O, H2S, H2SE, and H2TE, they are what? They are around the central atom. What is happening? They are having similar geometry, but irregular bond angles, because when we move from oxygen to sulfur to selenium and to tellurium, what is happening in the periodic table? The electronegativity actually decreases. See, electronegativity decreases from oxygen to tellurium around the central atom. So when electronegativity decreases, what happens? And if electronegativity is more, what happens? If electronegativity is greater, then the bond angle is greater. So what angle? Here it is AB2 type molecule, right? So having two lone pair, oxygen has two lone pair here. In the next, sulfur or selenium or tellurium has two lone pair. Now, what is happening? The electronegativity, if it is more than the bonded pair of electrons, then the bonded pair of electrons will move towards the electronegative atom a bit more. That means from the bond, OH bond, the electron density moves towards the oxygen atom. The electron density moves towards the oxygen atom. And now here it is becoming closer. Since it is becoming closer here, the repulsion increases and so the bond angle increases. Everywhere, in all the cases, there is lone pair repulsion, which is greater than the lone pair bond pair repulsion and greater than the bond pair repulsion. But then, what is the extra factor over here? The extra factor is the electronegativity of the central atom. When the electronegativity of the central atom increases, the bonded pair of electron moves towards the oxygen atom a bit more, and the repulsion between these electron clouds increases, for which the bond angle increases. So is what is happening in NH3. Electronegativity of nitrogen greater than phosphorus, greater than arsenic, greater than bismuth. So this is what I will tell you to see from this resource. Thank you all of you for being with me in this session. I hope it was useful. Please practice more and more questions in order to attain perfection. Thank you.